Guys. So, welcome to the second community call. We're really excited everyone's here today. Today we're going to be talking a little bit about the meta-analysis paper that me, Alexis, Zubin, and Maz have been working on for the past few months. And today we're going to start discussing the framework. So today's call is intended to be around 40 minutes. We'll go over the framework in about 20 minutes, and then we'll have some time for questions. Um, so one reason when I started doing research in the blockchain space, it was very hard for me to know what's objectively a good protocol or what's a bad protocol. Um, Oftentimes you see like people on Twitter saying, this is the best protocol, like EOS is very scalable. Or you hear Ouroboros saying like, yes, we can defend against all kinds of adversaries, but that doesn't necessarily make it the best protocol in any sense. And it doesn't make sense to say that there is objectively a best protocol. So I think a better way of thinking about it is saying, I have a specific use case, and for my specific use case, maybe I need availability over consistency in the case of a network partition. So using the meta-analysis framework, I can determine a best protocol for myself. And that's essentially what we wanted to do with this meta-analysis paper, which is create this sort of framework which anyone can use for their very specific use case or for anything that they're building on top of a blockchain and understand what best fits their need. Yeah.
Yeah. So kind of to go along with that, I think one thing that's really interesting is that as blockchains have come further and further along, we've kind of realized that there's a whole rich, like decades-long literature of distributed systems that kind of can really help us here. And so this is like all the work in classical consensus that has been pioneered over the last few decades. So a lot of the difference, though, between classical consensus and blockchain consensus is actually quite stark, and blockchain consensus is kind of a step change in this sense. So classical consensus usually worked in much more permissioned models. That means only certain nodes were allowed to write to the chain. They're generally much more centralized and work with much stronger leaders in their algorithms. In addition, what you see in classical consensus is like much more network homogeneity, and essentially what you need in a blockchain setting is you generally need attacks. You need some kind of defense against really strong attackers. So there's a much stronger adversarial environment. There's generally much more of a distributed environment, so there's less of a like one leader type algorithm that you would have in Raft, for example. And they're generally more permissionless. Like, for example, in Nakamoto consensus, anyone can write to a proof of work block as long as they solve the proof of work. So the traditional or classical field that worked with these adversarial environments are called Byzantine fault-tolerant classical algorithms or Byzantine fault-tolerant consensus algorithms, and they have really become a very hot topic for the blockchain space. The other thing that we need to look at when we look at these new algorithms in alternative consensus is their network models, right? So you can see that, again, in a very centralized classical system, you might have all the wires being the exact same, and so the amount of time it takes for a message to permeate the network is can be defined. All messages are gonna permeate the network in less than 10 seconds. But in a blockchain system that uses the internet and a more unreliable medium, you can't exactly say that. And so these different protocols are different also in that they have different network synchrony assumptions. Like, you can go all the way from synchrony, full perfect synchrony, where there's a specific upper bound on how long it'll take for a message, to partial synchrony, where this upper bound may exist but nobody in the network knows it, to asynchrony, where there's no upper bound on how long messages may take. Messages may never arrive. So that's another way that you can look at trade-offs, and it's very hard to say there's one optimal algorithm because they all assume different things about the network and classical model.
So network and synchrony assumptions are one thing. The next thing that your protocol needs to think about is what kind of adversary can it tolerate, right? So a lot of different protocols can only handle like an adversary that goes offline and online, not necessarily an arbitrarily acting adversary. A protocol that is truly strong should be able to handle some amount of like a Byzantine adversary which acts in any arbitrary manner. So when protocols talk about their adversarial model, you often hear terms like mildly adaptive, strongly adaptive, static. What do these even mean? Um, also, hey,
We have a new
we're a
incomer.
new person who's joined us. Yeah. Um,
Oh, don't worry, I'll just put it back.
yeah.
Yeah, no worries. Okay.
So, what even do these adversarial models mean? So, one way that I think of an adversary is there's this individual who's sitting on the network and takes some amount of time to send or to like DOS the other validators or other nodes in the network. The amount of time that this adversary takes to attack the other nodes in the network determines the strength of the adversarial model. So if that is instantaneous, it's a very, very strong adversarial model. If it's like zero, if that time is zero, then it's a static adversary. And once a protocol has started, they basically cannot attack or like DOS any of the other participants. And that's very important to consider in speaking about your adversarial model. A mildly adaptive adversary is just like somewhere it takes you between 0 to infinite time to corrupt other nodes in the network as an adversary.
So the next thing to consider is the economic model. So because we have these proof of stake systems where different validators are staking in and staking out, it's important to craft incentives such that you maximize the cost of any sort of attacks and incentivize honest validators to follow protocol. The issue is that the majority of these alternative consensus protocols that we've looked at don't specify a complete incentive scheme or complete economic model. So because that was the case, we weren't able to really fully comment on their economic model since most of them haven't been completely defined yet. In the case that we do have a defined economic model, there are a couple ways that we can try to look at it. One is to see if it's incentive compatible via a Nash equal. Caveat there is that you're only talking about rational actors, and in a lot of these cases, you're actually going to be having irrational actors. So it's important to try to come up with a scheme that takes that into account as well when you're organizing incentive models. Another interesting thing is that a lot of these systems operate in more than one round. So you might have one round of consensus, and that's a game in itself. But at the same time, when you have multiple rounds of consensus, you're looking at a multi-round game. So all of these questions relating to how to design an incentive scheme and then how to analyze it via a single round game, a multi-round game, dealing with rational actors and irrational actors remain open questions. So the next thing we wanted to talk about is how we kind of broke down these different protocols. And so we looked at the specific way that each of these protocols do consensus in four steps. So we looked at proposer and committee election and randomness generation, propagation, finality, and handling churn. And why these 4 steps? Well, they pretty much relate to the way in which consensus operates starting from beginning to end. So the first thing that you need to do is create a block. And who creates the block? In this case, your proposer is creating your block. And then what happens next? You need a committee to be able to verify your block. And the way that these proposers and committees are traditionally chosen is via some source of randomness, which is why we look at this first. Then what happens next in the process? Now that you have your block, you need to propagate it to the rest of the nodes in the network. And that's why we look at propagation next. Now, once every node on the network has the block, the next thing is finality. How do you determine when a block is to be considered final? And if we want these blockchains to be immutable, finality is really important. And then after that, handling churn. Because of the permissionless nature of blockchains, they should be able to handle both validators and users coming in and out of the network. And different protocols handle churn in different ways.
Okay. So when you have any sort of protocol, you want some way to select some subset of the users to be in your committee and to be verifying the protocol. If you have everyone participate in the verification in every single round, that's a lot of messages that are passing through your network. It's very expensive, and ideally, if you want a decentralized protocol, you want to keep it as scalable as possible as well. So you want to have some process of selecting this subcommittee of people. And that's where randomness comes in. So in selecting your randomness scheme, there are a few considerations that you should think about. The first is you don't want anyone in your protocol, any validator or any node, to be able to know ahead of time what the randomness output is going to be. And this is basically what we call predictable. If someone knows ahead of time what the output of your randomness generation scheme is, then your protocol is no longer truly random. The second really important property that you want to have is that none of these validators or participants should in any way be able to change the output of this randomness scheme. So in a way, they shouldn't be able to tamper with it and bias the output. And this is what we call the biasable property. But a lot of protocols think about both these properties, but they don't necessarily think about the third, which is revealing the seed before the current round. So if you reveal the seed, the randomness seed, before or ahead of time, then the proposer or the subcommittee can be determined ahead of time, which means other validators or other people as part of the network can attack the subcommittee and like DOS them. And this is very important because this makes a protocol less permissionless in a sense, because it puts a responsibility of creating some sort of DOS resistant validator or an attack resistant validator on the validator on the person who's running this validator, which means only someone with very good software engineering skills can now run a validator or like even be part of the network if they want to be like not attacked or not DOSed. And the whole point of having a permissionless system is to ensure that anyone can join, not just software developers and like people with technical skills.
Yeah, and kind of to go off of that, and we should talk a little bit about the results and analysis, which is like part 5 of the paper. If you see table 3 on page 12, you can see that since there's 7 different protocols and there's 3 different actual things we looked at in this section, there's like 21 different combinations. So we're not going to go protocol by protocol, but we'll give you the general results that we found. So in terms of finalization guarantees, of course, this goes along really kind of well with what we're talking about in section 2. What we found was that the more traditional type of protocols, the more BFT, Byzantine fault tolerant type of protocols, generally have stronger finalization guarantees than the other protocols. Chain-based protocols, of which there are a few that we looked at, are generally more based on like weighting the chain. So of course in like Nakamoto consensus, you weight it by the length of the chain. You can weight it by the number of coins staked on that, and that's like more of a probabilistic finality rather than absolute finality that you would look for in a BFT algorithm. And this will also kind of relate a little bit to the future. I'll talk in a second about like availability versus consistency. Generally, the consistency favoring algorithms like Tendermint are going to have stronger finalization guarantees as well. Now, scalability is obviously something really important, and one of the main reasons that people are trying to move towards proof of stake is so that you can have some kind of scalability. There's 3 main parts of this. First is, how does the algorithm get better as the number of nodes increase? The second is, how does it actually appear in the blockchain? How fast is the number of transactions per second? Unfortunately, because none of these algorithms have been used in a permissionless setting and in a large distributed setting in the real world, other than, of course, like proof of work, there's no real good numbers. And so a lot of these numbers are speculative at best. So that was a little bit unfortunate, but I think it's a very interesting point of research. If anyone wants to do like actual simulations of these algorithms, that would be a really, really good set of metrics to track. The next thing is handling churn. As Alexis said, obviously people are leaving and joining the protocols very quickly. Now, certain algorithms are better than others at this. So the more traditional BFT algorithms that I talked about earlier that are more finalization favoring generally they don't handle churn as well because they're made with a more static set of nodes that are like verifying, that are proposing. Of course, this static set of nodes is there's some kind of algorithm where you can change what nodes there are, but it's generally more difficult than in a sleepy model, like in Thunderella or in a lot of the sleepy based or completely permissionless setting algorithms, which generally have better ability to partition. So, kind of going back to what I was talking about earlier, Eric Brewer has this is that in the presence of a network partition where parts of the network cannot actually interact, they can't send messages between each other. There's either the priority of consistency or a priority of availability. You can't have both consistency and availability in that network partition case. And what you find, again, is the more finalization favoring algorithms, the BFT algorithms, are more consistency favoring as well, and the other algorithms that are more permissionless are more availability favoring, which is very interesting as well. So that's kind of section 5.
Okay, so that's pretty much the framework we're going to be using to analyze all the protocols in the future calls. We've had a lot of people from the community engage with us, and this is where we want everyone to participate. We've had Vasily and Alberto start working on Avalanche and analyze it from a very similar framework. They should be adding it to the paper very soon. If you guys have any other protocols that you, a good way to learn about a new protocol in such a way that you'll like deeply understand it, you'll never forget it for your life. And it's also a very useful community resource. What we want this to be is, of course, something which is really accessible to everyone out there. And anyone who wants to ever design their own protocol or analyze existing blockchain protocols should be able to use this. So, do you guys have any questions now about the framework? Next week, if there are any demands, is there any specific request on what protocol you guys want to look at next week? If not, we can look at Casper FFG, Vitalik's Casper. Anyone?
I don't know if you guys can hear me.
Yeah.
Oh, yeah. I don't really have anything to add, because I'm kind of just learning about this stuff all myself, so I'm just like kind of staying quiet and like learning from you guys and everyone else in the community. But yeah, I'll definitely be here next week for whatever like implementation, for whatever protocols you guys choose to do. And I just wanted to thank you guys for doing this too. Like, I think it's great. Like, I don't know. You guys, it's a lot of work, and I appreciate you guys doing this. So.
Thank you.
Thank you so much. Yeah.
Yeah. We hope you can we hope that people learn things, because when we started, there was a lot less resources out there to learn about this kind of stuff. There was really only Casper that was out then, and not too much documentation on it either. And now there's like a really cool literature. So
yeah,
love to help out in that way.
Yeah.
Are there any other requests on what we should cover
On my
next
side, I don't have any other questions, but I really like the initiative that you guys have taken this, and it's really helpful. And I'm actually started learning about the blockchain and then trying to understand different type of protocols that we have, and the networks and the infrastructures. And this is my first connect with the community, though I'm in crypto for the last 1.5 years.
Nice.
So I'm really glad that I found someone where I can actually even learn together and then share the knowledge and then grow. Thank you very much for initiating.
You're welcome.
Thanks. Yeah. We want this to be like as helpful to the community as possible, of course.
Oh yeah, great. Thank you very much for the good thoughts.
Any other questions from anyone?
Algorand would be cool.
Do you think you could explain a little more about your organizational structure? So, like, you describe yourselves as an open source research group, right?
Yeah.
But, like, what does that really mean?
Right. So, when we say open source research group, it means, like, we put all of our work right from start to the end on the GitHub repo. Like, I know, for example, when I started research, I'd like to track my thought process to be versus what it currently is. like if, for example, I had the access to a research mentor, then I would know how their thought process on like analyzing protocols changed over time. But it was very hard for me to reach out to these people. So something that we want to do is like create this sort of repo or this place where everyone can contribute and they can track their own thought processes over time. Other people who are learning can understand how other people thought and how those thoughts evolved over time um, as they go through this process of research.
Yeah, and it's also like a very big like community aspect of it because I feel like, as Aparna said, a lot of the people in this space that are experts are, sometimes they're very busy. There's all sorts of I guess
Yeah.
it's very hard to get into touch with a lot of the people who created these protocols and of course that's something we want to kind of have like a more open community feel where if anyone has a question on any protocol, anything they're learning about, any thing they're stuck with, that you can just direct questions to us. We have resources and we would love to help in that.
Yeah, and I think the other
Do you
thing
guys-
is like collectively working together to produce actual research. There's a lot of people around the world who are very interested in this stuff, and sometimes it's hard to find a group of people who are interested in the same problems. This can be a way to do that, and then to conduct that research open source and in a structured sort of framework through the Mechanism Labs model.
Yeah.
Do you guys go to Berkeley? I saw the shirt.
So we used to be executives in blockchain at Berkeley, and then I graduated, and Aparna, Teal Fellow, had to leave school, kind of. But then Alexis Galva goes
She goes to
Berkeley.
Berkeley. She goes to Berkeley.
And then Mazuddin is also a Berkeley graduate up there.
Yeah.
There's some Berkeley people on this call. I think Sunny and Dave were here. I don't know if they're still here.
Sunny doesn't go to Berkeley.
Hello.
anymore.
Yeah, Sunny. Yeah, Sunny. You don't do Berkeley, do you?
No. I live in Berkeley, city Berkeley.
Dave goes to Berkeley.
Hello.
Oh no!
Yeah. Any other questions?
Can I add something?
Yeah, of course.
Hey, so thanks for doing this. I was just wondering that if you are planning to look into individual protocols, then can we start with PBFT, like practical BFT, the paper? Because I have tried to I think that's the basis of all like BFT problems solution, and I've tried to go through this many times, but I still don't think I have complete grasp over it. So I was just wondering, rather than starting with POS sort of models, can we just start with PBFT? I think the paper by Likov is the standard paper for that.
Yeah. So actually,
if we go through that, sorry.
yeah. So Dave Oja, who's on the call right now, he has a video on YouTube explaining PBFT. It's like the most easy, simple explanation I've ever heard. I'll try to link it. I'll try to link it on on the Telegram or whatever. But Dave now has a face. Now Dave is a real person.
Sorry, Dave, we leaked your privacy.
Yeah. So Dave, he has a good video on PBFT, so I can link that as well.
Yeah.
Uh,
We can
I'd
do
also
that.
recommend looking at Tendermint because basically you take PBFT
Yeah.
and you remove the very complicated leader election process and view change thing, and it's just an easier way to use PBFT with a blockchain.
Yeah.
Yeah.
Tendermint is like definitely a very classical model of consensus
Yeah.
algorithm, like PBFT stuff.
We could potentially start with Tendermint next week, if that's of more interest.
That would be right.
Okay.
Dave Oja, Sankalp, you want to help
Dave-
us with that?
Yeah.
Yeah, because they work.
They're
work
the
at
protocol
yeah,
designers.
they work at Cosmos and stuff. So. Okay.
Sure.
Okay, that's great. Okay.
Okay.
Okay. Any other questions?
Earlier you were saying something about you can't you don't want to know the proposer too far in advance. and you'd like there to be basically the whole network be proposers. But I'm not sure if, like, say in the Algorand model, right, where it's weighted by stake, you can still like DOS people with higher stake. Like, if you can still target based off that. It's not like anyone who joins network has equal probability. That's not simple
correct.
resistance.
But then let's say you DOS everyone in the world with higher stake than you. Well, there's still going to be a lower stake proposer who's been chosen, even if they have like a lower priority, according to like the Algorand model. There's still very high likelihood of someone who is chosen as a proposer with lower stake than someone you DOSed. So then they'll.
Okay, that's a fair point.
Yeah, Algorand is like pretty interesting. So, but there's definitely like problems and ups and downs of it.
Yeah.
They patented using VRF for committee selection, which is kind of interesting.
Open source.
Well, the solution here is just found your blockchain in a different country, not the U.S.
A place with low patent law.
Switzerland?
LMAO. Anyways.
Okay.
Any more questions, thoughts, comments, concerns?
No.
All good? Okay.
Okay, if not next week,
Or next 2 weeks.
next 2 week. No,
2 weeks from now?
2 weeks from now.
Yeah.
What am I saying? 2 weeks from now, Dave and Sunny are going to be helping us present Tendermint from this framework.
And yeah, until then, like,
And-
there'll be lots of discussions on the Telegram and stuff.
Yeah, join our Telegram, start discussions with other people. If you want to contribute to the paper, just ping us on Twitter, on Telegram, and have conversations. If any of you come out with any interesting ideas that you want to start your own repos on, we can facilitate that as well. Yeah.
Also, Mazuddin needs a haircut.
Growing it out.
What?
Growing it out.
Growing it out. Okay, I see.
Okay.
What's the Telegram called?
Search Mechanism Labs, and you should be able to find our GitHub. The Telegram's linked only on the GitHub because we want people who want to actually contribute and have technical discussions on the Telegram.
Oh gosh, okay.
Yeah.
I'll join, but I'll stay in the back. But thank you.
No, we do want people who want to learn as well. We just don't want like scam. Yeah.
Yeah.
Sweet.
Okay. Cool. Thank you all for joining today's call. It's exciting seeing everyone.
All right. Thank you very
Thank you,
much.
guys. Thank you, guys.
See you next week.
Bye.
Bye.
See it.
It's a stop video. How do I stop
End
it?
meeting.
Okay.